what we're going to talk about today. So you should have recognized that new topic, new law of physics, I guess, for lack of a better word. And you see, I got dangling from my head here, spring on a little support. I put a meter stick right next to it. Not sure how well you can see the meter stick. You can just trust me on the numbers, I suppose. And what we learned about springs in the pre-lecture reading and video is that if you pull on a spring, it pulls back. Pretty straightforward thing right there. And so it's bouncing around right now. Let's hang. This is a 500-gram mass, and it's sitting right about 66 centimeters roughly. And I drop it with a 500-gram mass. That's a half a kilogram, right? So the force I just pulled down, you can do that math in your head, 9.8 meters per second squared times a half of a kilogram, 0.5 kilograms, it'd be 4.9 newtons pulled down. But you notice it's at rest right now, right? Not bobbing around. So that means the spring must have be pulling up at 4.9 newtons as well to keep it at rest to the degree it's bobbing around that I can damp it out. But you notice in order to do that, in order to pull up with 4.9 newtons, the string got longer. The spring got longer. I'm sure I enunciated that P correctly. Okay, and so it went from what I said, 66 down to about 40 centimeters. It's just the way I've got the meter stick oriented. That's a change in 26 centimeters from where it was unstretched to when I put 4.9 kilograms on it. Okay, let's see how linear this spring is. I got another 500 gram mass. So now I'm hanging a full kilogram on it. And so now there's 9.8 newtons pulling downward, the weight. And you may not even be able to see that right there. There they are. Okay. And the spring is pulling up with 9.8 newtons because it's at rest. Some of the forces have to be zero. And it's gone down to about 14, stretched about another 26 centimeters. Okay. And so the guy who was credited with looking at this aspect of springs with a P, okay, was Hooke, and we learned about his law last night. And I'm going to start sharing with you my PowerPoint. I only have one polling question here. It's numerical, and I'll put a little equation. Is it there? I'm not sure you're seeing that. I normally see a green border, so let's try one more time. And there, no, that's desktop. 8.2 elasticity, shear. Now I see the green border, so you're absolutely seeing it now. And this spring on this question happens to be horizontal, right? And what somebody did is not just unstretched, one mass, two mass. Somebody did a whole bunch of data points right here and plotted them, okay? And remember, so I don't know, I did two. Somebody did a whole bunch and drew a straight line. Hooke's law says that the force provided by the spring is equal to minus the Hooke's law spring constant times however much the spring length changes. Now, I did it vertically, so I would have put delta y. This particular question, it's horizontal, so you might like to put delta x instead. And remember, that's a change. It isn't an absolute length. It's how much the spring length changes from its final to its from its initial to its final. So delta x is always final minus initial. I want to say one word about this negative sign. Don't take it too seriously. Remember, in physics, often we use negative signs to denote direction. A positive force is often either up or to the right. A negative force is often down or to the left. We started talking about torques. A positive torque is going counterclockwise. A negative torque is going clockwise. And so our use of negative signs is really just to denote direction. And in this particular case, realize if your displacement is that way, okay, delta x is your displacement, all this is telling you is that the force that the spring puts on this mass is in the opposite direction. That's all it's there for, to remind you of that fact. And if you got that, you're good to go. Okay, so when you're using springs in free body diagrams and maybe a force like in my vertical case here where I had the spring oriented this way, and I look and I go, well, there's a weight force right there, and that's supposed to be vertical. That's pretty lousy vertical, but hopefully you get the point. We'll straighten it out a little bit. There it is. Straighten that out a little bit. When I look and I go, the sum of the forces, the net force, I will go equal to the force of the spring minus the weight, and I say that's equal to 0 because the thing was at rest. Don't go putting that negative sign in right there. The direction of the force on the spring is based on what direction it's pulling. In this case, upward, so you'll leave it positive. The negative sign is only there to remind you that the force is in the opposite direction of the displacement. The force of the spring is in the opposite direction of displacement. Any questions on that? Any questions on anything we've done? All right, so I've been letting you stare at this picture here for a second. And so now I'll open the one poll question I've got for this morning. And it's always at the bottom of the list. Scroll to the bottom, launch the poll. Maybe you figured out what the value is for the spring constant. Yep, 5 of you jumped right on the right answer. You're probably kind of looking at it while I was doing it. And I left it as fractions just so you wouldn't have to grab your calculator. So it's 2/5, a 1, 2/5, 5/2, 4/5, or 5/4 is what I'm showing there. I generally like to do fractions vertically with a horizontal bar, but obviously couldn't type that into the Zoom system. All right, got 25 people. That's a great quorum. And the majority have it right too, so I'm happy with that. And looks like we'll end it here. Probably somebody on a cell phone or something can't participate, so I'll end it. I will share it with you. And the majority got the right answer, I think. Look, if I just pick any 2 data points, like I did in my case, you could, from the numbers I gave you, I could have calculated the spring constant of my spring sitting right here, right? But let's pick 2 points right there and right there. And I look and I go, well, solve this, and I'll go above it. Hooke's law spring constant is equal to the force of the spring divided by the displacement. Okay, and so there's X, there's displacement. Force of the spring was minus 2 newtons if you want. So if you could probably put that negative sign back in this particular case. So it's minus 2 newtons. And then the displacement of that was 5 meters. And so in this case, you can be rigorous with that sign if you want to. I have no problem with just thinking of it as an absolute value. Okay, but you notice the answer is 2/5, and the units have to be newtons per meter. And we just leave them that way for Hooke's law spring constant. So B is absolutely the right answer. So great job on that for about half of you that went that way. One of the things that some of you might notice, if you were good with linear algebra and you like graphs and Cartesian coordinates, you could see that what Hooke's law spring constant is the slope of this line, isn't it? And it actually is, in this case, graphed as a negative number. So the slope right here, that's the slope of this line. And it is negative, okay, with that negative sign. And now all that's saying is if I pull the spring in the positive X direction, the force is going to be negative because it'll be in the negative X direction to the left. I pull to the right, it's the force of the spring is to the left. So if we were to do a lab next week where I asked you to measure the Hooke's law spring constant, if I just had a spring and put a whole bunch of different masses on it, told you what the force of the spring must be in order to balance those masses, you could certainly figure out what this Hooke's law spring constant is, doing exactly this. All right, last chance for questions on Hooke's law, because I'm going to talk about something real new here. I'm going to do a problem, and then you've got a number of short problems here to do on the worksheet. And I should be able to give you enough time to finish it right here in class for a change. Questions? I'm going to stop sharing, and I want to go back I don't have a question on this. I just couldn't find one on relating Hooke's law, not to just springs like this thing, okay, that I've got hanging here, which I'm going to get out of the way so I don't keep banging myself in the head with it as I work problems. So let me pull this guy out here and put it on the floor. Hopefully my dog won't take that away. I think it's a stick for her to play with. Anyway, hopefully you're seeing a, now not a spring, but just maybe a metal bar or wood bar or something like that. Heck, this could even be bone, as you saw in the pre-lecture video. We can do problems like this with bones. And there is such a thing as a Hooke's law spring constant for just solid one-dimensional objects like this, sticks, rods, bones, whatever, okay? And the effective Hooke's law spring constant is related to an engineering number called Young's modulus. So we give it the symbol Y. In some other classes, I've seen it given the symbol E. This is a very common engineering modulus, I guess. Okay, all it is the relationship that allows you to calculate what an effective spring constant is for something that'll stretch. And everything stretches a little. We assume in a physics class, we've been assuming up until now, that any strings we have attaching to masses, they don't stretch. But in reality, they do, just a little bit in some cases. In some cases, for more rubber band-like material, it stretches quite a bit, right? And so anyway, Young's modulus would allow me to calculate what the effective spring constant is. All I do is I multiply it by an area. If you look at our table here, these engineering modulus called Young's modulus, by the way, you can go to CRC handbooks, literally pages of engineering modulus for various metals and elements, anything that we can turn into a solid. Somebody has probably put on a testing apparatus, stretched it out a little bit and figure out what Young's modulus is and published a paper to get it into their CV. Anyway, Young's, and we just got 6 or 7 things, right? What is it? 8 things here. Big numbers. Units are 10 to the 10th Newton per meter squared. And so that's the thing you got to remember. For any of these numbers, you got to multiply it by 10 to the 10th. And the units are Newton per meter squared. And so if you take that and you multiply by the cross-sectional area, and what we're talking about is that cross-sectional area right there. And hopefully everybody knows that if it's circular in cross-sectional area, the area is pi r squared. But I have seen people over time, people who've taken calculus even, not be able to remember that cross-sectional area of a circle. So there it is. That's our cross-sectional area. If it was square, you'd use length, like a rectangular cross-sectional area, you'd use a length times a width, but just an area. And then you divide it through by the length of the thing. And so if you look now, the numerator has units of newtons, the denominator has units of meters. Newton per meter, that's what his Hooke's law spring constant is. So although there's no rigorous proof of this, by dimensional analysis, I think I've shown you what the Hooke's law spring constant has to turn out to be in terms of Young modulus and some dimensions of the object that we're stretching. Now, it's auto-saving for me. Great. I will say one other thing about this Young's modulus. A kind of an easier way to remember this is that stress, and this is the way the engineers define it, stress is equal to Young's modulus times strain. Of course, if you remember it that way, you got to remember what a stress and a strain are. And again, I'll look at units. A stress is like pressure. A stress is just the force that is being applied, or the force which is being restored by the stretched object, like the Hooke's law spring force is opposite the direction of the weight. So that stress is a force divided by a cross-sectional area. Those of you who are chemists or have studied some chemistry, you recognize that's exactly the same unit of pressure, right? A force per area, a Newton per meter squared, a Pascal if you like, okay? That's what a stress is, force per unit area. And so that is Young's modulus. A strain is an interesting thing because if you look, stress is force per unit area. Young's modulus is also force per unit area. Strain must have no units, and it doesn't. It is the deformation length, that change in length that the object undergoes. You can see it's this little length right here, change in length, delta, final minus initial, again, delta anything, final minus initial, over the original length, okay? So I said stain. Boy, that's pretty sad. I've just finally noticed it. I appreciate you guys not laughing at me too bad about that. But that should say strain. Strain. Okay. And so strain is the change in length right here divided by the original length. Stress is the force that I either put on it or that it pulls back with, because in equilibrium, they're the same, divided by the cross-sectional area. The relationship between those two things is Young's modulus. Okay. And you can see if I just zip those constants around here, if I take the force that used to have an area underneath it and bring the area over here, okay, and then right there I've got strain, you can see that what I wrote right here and what I put in the pre-lecture video and the PowerPoint, which is of course available. I got this as a PDF if you need these notes. You got it. Okay, it's the same thing. I would recommend, if you don't know these two relationships, force is equal to Hooke's law spring constant times, that's supposed to be a delta x with a negative sign to remind you that they're in the opposite directions, or this one. And, if in the same spirit, I might have a negative sign right there, because the direction of the change in length and the direction of those forces are the opposite direction. You can think about magnitudes if you want, but that's what that negative sign is there to remind you. If you don't know these two equations, write them down. They're simple, just plug and chug, and that's what you're going to have to do on the worksheet today. But I'm going to do a couple example problems first. Any questions? All right, then I'm going to finish sharing this with you. If there's any questions, now's the time while I'm changing my share with you. I'm going to go over to Notability, where I've got a problem set up. And those of you that are thinking med school in your future, problems like this show up on the MedCat. This is where this problem originally came from. And so let me share my iPad with you. Okay, you do the screen mirroring trick. Come on. All right, there it is. And put that away. And hopefully you're seeing today's worksheet, 8.2. And I'm going to do the first, I'll set up the first one. And then you all, unfortunately, they're all pretty short, so you got to do all three, okay, of the problems. And you see somebody's arm here holding that mass is supposed to be a bowling ball, pretty heavy, okay? And you can see where the person's bicep is connecting to one of the arms, one of the bones in their forearm. Okay, it hooks up to the shoulder somewhere. I don't much care about that. You can see at the elbow there's a contact point between the two forearm bones and the bone that's next to your bicep. And some of you are probably laughing because I can't come up with a name of what those bones are. If you studied this, you're way ahead of me, but I can do the physics problem. Okay. And the question I guess we want to figure out is, if that bowling ball has a mass of 7.2 kilograms, and the forearm, the bones and the skin and the tendons and all that in the forearm has a mass of 1.8 kilograms, and we'll assume that it acts right at the center, what we've been calling the center of gravity of the forearm. So we'll give you that dimension. We'll assume the weight acts right there. Okay, it's a reasonable assumption. I want to draw a free body diagram of the forearm, and I conveniently made it horizontal because making it at some odd angle will just make the problem hard for no real good reason. Draw a free body diagram, and then we got to figure out what force the bicep has to pull with in order to allow your arm to hold the bowling ball horizontally. Okay, and you can see that our biological makeup isn't very efficient from the point of view of torques, because that thing is pulling so close to the axis of rotation right there. Okay, it's not very efficient at applying a torque. It'd be kind of nice if the bicep was to come across near our wrist for this particular application. But then there's others that wouldn't be as good because you wouldn't have the flexibility, things like that. Any event, I've labeled a couple points here. Let's kind of draw what we think all the forces are. Obviously, the bowling ball, and I think I call that mass big M. So there's big mg. There's the weight of the bowling ball. We said the forearm mass, it's smaller, obviously, but that's mg right there. And I think the axis of rotation, we're going to make the elbow. That's logical, right? Your elbow moves about that axis right there. But the bone in the upper arm, the one that's parallel to the bicep, is actually in contact with the forearm bones. And so must be putting, that's not good. All right, it's back. Must be putting a normal force that way. I think a contact force where the two bones meet, there's surface that's in contact with each other, and it must be pushing downward. Okay. And I'm going to call the bicep force, you can call it whatever you want, but it's a tension really, isn't it? And that's what you do. You work with masses like this. If you're doing a bicep curl or whatever, this is kind of the horizontal position free body diagram, isn't it? Okay, any event, let's make a formal free body diagram though, with some distances. And so I'll draw it right there. And the normal force, we got no idea how big that is. Okay. The next thing, I guess, is that tension force in your bicep muscle. And I think I'll just put a dashed line here. According to the picture, and it's kind of hard to tell exactly, but that's 4 centimeters right there away from the let's go back to that guy. That's 4 centimeters right there from the elbow. Okay. So that distance right there, I would have drawn it this way in my diagram, but the book I stole that from, that's how it drew it next to it. But there's your 4 centimeters. Okay. Next number we got is the weight, little mg, the weight of the forearm, the hand, the skin, the tendons, everything acting right there. And that's 15 centimeters away. Okay. And then lastly, the bowling ball right here, the big mass times G, that's, I'll put it up here, 30, what does it say? 33. That's easier to read on my notes here. 33 centimeters is that distance. Okay, everybody see the picture? Any questions on the picture? I kind of drawn a free body diagram twice. Some of you might say, hey, I can work from this physical picture up here. And I don't disagree with you. It's just better technique to label the distances, have everything off separately so you can work the problem. And now, if this is at rest, what are our two conditions? Our two conditions are that the sum of the forces, force net, if you are allergic to that Greek sigma right there, the sum of the forces, and I guess these are all vertical. There's no horizontal forces here. Has to be equal to 0. And so let's add them up. That means the tension, which is up, has to be equal to, well, let's do it the correct way first. The tension, which is up, minus the normal force, minus m times g minus little m times g has to be equal to 0, right? And so I guess that tells me that tension minus normal force has to be equal to, I'll bring the two masses and the acceleration due to gravity, the weight of those two objects, I'll bring them to the other side of the equation, and I'll put in some numbers, and I'll even factor out the g, because g is 9.8 for both of them, right? And then I've got the big mass. Big mass was 7.2 kilograms. And then the little mass, notice I didn't put a unit there, I'll fix it in a second, plus 1.8. Those two add together, and I'll put the kilograms for both of those guys right there. Okay, I did that in my calculator before class. I got 9.8 times the sum of 7.2 and 1.8. That's 8, I guess 9. And so I got about 88 is what I got. 88.2 newtons. If you do the right number of significant figures. We'll do it. It's an intermediate calculation. I should round it to 88, but I want that extra digit for the next calculation I got to do. Problem, of course, is I got two unknowns there, right? I can't tell you what the tension is. I can't tell you what the normal force is. I got one equation, two unknowns. Can't solve it. What's the other equation? The other equation is that the sum of the torques, the net torque, if you like, has to also be equal to 0 if the thing is in equilibrium. And as I said the other day, strategically picking the axis of rotation at one of your unknown forces might allow you to have one equation with just one unknown. And so the choice of putting the axis of rotation right at the elbow not only makes common sense, but when I start doing torques, which is a distance times a force, well, the normal force has 0 distance, so it has 0 torque, right? And so the sum of the torques then is equal to 0 due to the normal force. And let's see, that tension will give me a positive torque because it's going counterclockwise. And I'm going to put actual lengths here. Oh, it's 4 centimeters. It's not 0.4. One of the common mistakes, 4 centimeters, 0.04 meters. times the unknown tension, okay? And that's positive because it's going to cause a rotation that direction. Now the negative forces, negative torques, forces which are calling negative torques, is 0.15 meters, that's 15 centimeters, times little mg, that's the mass of the forearm bones, the skin, the tendons, all of that. And then also the bowling ball is tending to cause rotations that way, which we've referred to as negative. So it's 0.33 meters, okay? And then times big mg. And yeah, that's great because I know both those masses. I know the acceleration due to gravity. I have one equation right here. The only unknown is the tension, right? So I can solve for it right away. And let's see, I'll put the numbers in. All these are negative, I guess. So I can bring them to the other side of the equation. 0.4, no, 0.04, because it's 4 centimeters, meters, times the unknown tension has to be equal to, put in all the numbers now, 0.15 meter, 15 centimeters, times, what was that, 1.8 kilograms, times 9.8. I could have factored out that, again, just to save myself a little bit of writing, okay, plus, let's see, 0.33 meters times 7.2 kilograms times, again, 9.8 meters per second squared. And I put all this in my calculator. And let's see, kilogram times a meter per second squared, that's a Newton, times a meter, that's a Newton meter, which is a good unit of torque. And I added all those up, I got 25.93 Newton meters. And you can check me on it, okay? Hopefully you can see why they became positive, right? When they were on the left side of the equation, they were negative. That's all equal to 0. So when I brought them to the other side of the equation, they became positive, and that was my answer. And so I guess the next thing, and I'll give myself a little more room to finish the problem here. The next thing then is what I really wanted, which is the tension. The tension then is 25.93 Newton meters divided by 0.04 meters. And you can see the meters cancel. I'm left with tension in newtons, exactly like it has to be. And when I did that division, I got a big number, 648.3 newtons. Let's just call it 648 newtons. So your bicep is actually putting a fairly substantial force in the upward direction, right? That would be roughly the equivalent of picking up a, I don't know, 65 kilogram mass. That's pretty big. Think about what the plates are that are 45 pounds. Okay, they're pretty big, 20 some kids. So this is a fairly substantial tension that your bicep is putting on your forearm bones. Okay, so but we haven't answered the last question. What's the normal force? But hopefully that's pretty straightforward. If I know that the tension minus the normal force is 88.2 newtons, I'm going to finish it up down here. Tension, which I now know to be 600. Come on, let's get a good pen movement. That's highlighting, isn't it? I hit the wrong button. There it is. I still want to make that go away too. Tension minus the normal force is equal to 88.2 newtons. And I now know what the tension is. So that's a good deal. I can go then that the normal force, and I'll solve for it algebraically, I guess. The normal force is equal to the tension. Yeah, it is tension minus 88.2 newtons. And so that's 648 minus 88.2. Legal, bring out the newtons because it's in both terms. And when I did the math on that, I got 560 newtons. So the elbow bone is also pushing down, the upper arm bone is pushing down on the lower arm bones with a normal force that's fairly substantial as well. And so there are the two answers to my question. Any questions on what I did there? If you think about it, I did a problem on Wednesday. Now today is Wednesday. A problem on Monday where I just looked at a plank and I did pretty much the same thing. So this is kind of important for its medical application. It could be about levers and things like that, teeter totters, but it also is bones in your arm and how your muscle skeletal system work together to allow you to do things. All right, here are the next three problems, which I guess I notice. How did I get 2 1s? I did the first one. You're going to have to do pretty much what you did on the first pulling question. You're going to have to look at, okay, so we pull with 4.9 newtons. The thing stretches 12 millimeters. The big mistake people will make there is 12 millimeters. No. Big mistake there is I'm using a highlighter instead of a pen. 12 millimeters. How many meters is that? That's 12 over 1,000, isn't it? Meters. So that's 0.012 meters. That's the big mistake people make. And then once you've got the Hooke's law spring constant from those two numbers, now figure out what the force the spring would exert if you then stretched it 17 millimeters. So that's the first problem. All right, and the next one, this one you'll be using that Hooke's law. What's the stress? What's the strain? What's the Young's modulus, which is related to Hooke's law? Okay, and remember that stress is force per unit area, as I'm saying right there. The elongation is just that delta L, but then the strain is delta L over L. And I meant to put that right there, but didn't, just forgot. And pay attention to units and powers of 10 here. And then the last problem, if I can get the right tool, talks about ultimate yield strength. Okay, and notice what that is that's a stress, right? Given is 170 times 10 to the 6 Newton per meters. So really what we've given you is a force per area. And we're saying that the cross-sectional area of the femur bone in this case is a given number. And so I could have made you take that diameter, that radius, I guess. Is that a radius? That's a diameter. And I could have made you calculate the area. I'm giving it to you. So just remember that force per unit area is equal to a stress. And this ultimate strength of the bone, that's the stress at which it breaks. Okay. And so figure out what the force must be that would cause it to break from the cross-sectional area. Any questions on that? All right, well, I'm going to break you up just so that I can jump around and talk to people in smaller groups. And so hearing no questions here, let me go. It hid breakout rooms. We got, what do we got here today? We've got 28 people. We'll go 7 groups of 4. And everybody's working on the same 3 problems. They're all pretty short, quick into your calculator. Go have fun with them, and I'll be jumping around groups answering questions. If you need me, because you're stuck on something, you can request and I'll jump right to your room. See you in a bit. All right, you guys are still hanging around for some reason. I'm jumping to the first group to help out. All right, anybody got any questions? Everybody happy?
Yeah, I'm all good.
All good? Yeah, these aren't terribly difficult. When we come back in, I'll make sure everybody's got the numbers so that they can check their work before they turn it in.
Thank you.
How'd that happen? Try and All right, anybody got any questions here? Everybody happy?
I'm working through it now. I'll call you if I have any questions.
Sounds good. Then I'm gonna go on to the next one.
Thank you.
You bet.
I have a question.
Sure, that's why I'm here. What can I do for you?
So for the second number one,
Yeah.
for part B, you're not supposed to use the same K as part A, right? Because
Yeah, once you found it in A, you can
It's
use
the
that.
same?
It's the same because the spring hasn't changed, right?
Oh, okay.
Right. See, so a manufacturer makes a spring, it has a spring constant. Every one you ever have in your car, the springs, the one in your ballpoint pen, they have a particular spring. So in A, you calculate what the spring constant is for that spring, and then you use it again in part B. So yeah.
Oh, okay.
So what'd you get for
Thank
your spring
you.
constant?
408.
Sounds good to me. And so
Okay.
then now you just have to multiply it by a new displacement.
Okay, thank
All right.
you.
You bet.
For number 2, I got -408 and -6.9. Is that correct?
Yeah, that looks good. And the negative sign, what does that tell you? That the force is to the left, I guess.
Yeah.
Okay. And the Hooke's law spring constant we generally think of as an absolute value.
Okay.
So you just make that positive 408. All right. Move on to the next one.
And then for the A, for the strength, I got 2.18 times 10 to the 8th.
Sounds good. What's your units though?
Newton meters squared.
Newton per meter squared.
Newton
divided. Yeah, divided by meter squared. Okay. Looks good. Any questions for you guys? You folks, I should say, I guess. Although my wife told me that guys is just a gender neutral term. She's always used it. Good to go?
Yeah.
All right. I'm going to go to the next room if you guys are working well.
Dr. Tukolsky,
Yeah.
I was wondering what equation do we use for part B in number 2?
Okay. Yes. Let me share my whiteboard with you guys. And remember, we said stress. That's a lousy looking E, but is equal to Young's modulus times strain with a R. So it's not stain, it's strain. Okay. And we said stress was a force over an area. And that's equal to Young's modulus times we said strain was delta L over L, right? I think in that equation, you know everything except delta L, right?
Okay.
You know what the force is. You know what well, you're gonna have to calculate the area, aren't you? That's probably the hardest part. You got to get. Do I tell you the area? Do you have to calculate it from a radius? Now you got a radius, don't you? And so you're gonna have to calculate the area from that. Pi times the radius squared. Okay. And then Young's
Okay.
modulus is given and length is given. All right.
So what are the units for stress?
Units for stress right here. It's a Newton divided by a meter squared. And if you
Okay.
look, Young's modulus given also a Newton divided by a meter squared. And the reason is because change in length is in meters and the original length is in meters. So that thing is really dimensionless, right? That's a lousy looking M there. That hopefully looks more like them. So these two things have exactly the same units, don't they?
Okay.
Yeah. All right.
Thank you.
You bet. That's probably the hardest problem of all of them on the worksheet today, right there. All right.
On the PowerPoint, there's K effective, but I don't think that's
Yeah, that's what you want to use. That one right
Oh, it
there.
is?
Yeah, you're in number 2B.
Yeah.
Yes.
Yeah, that's the one I've been getting all the questions on. That's why I'm so late getting to you guys' room. Sorry about that. Here, let me share my whiteboard with you. Oh, it took it away. Here's the deal, though. We said that force over area, and this is when we were getting the K effective. So you'll see the same, the equation just moved around a little bit, is Young's modulus times the change in length over the length. The only thing you don't know there is that change in length. The problem gives you the force. It doesn't give you the area, but remember we said the area is just going to be pi r squared. Young's modulus, you know, and the length, you know, so you just got to calculate that one. This is probably the hardest one on the whole worksheet right here. All right.
Okay.
Sounds good. I'm going to, if you're right there, you're going to, the last one is really quick. Number 3 will take you 2 seconds, but work on that one and I'll bring everybody back to the room so we can put out what the answers are so you know how to compare. All right.
Okay. Thank you.
Guys later.
Okay, so then it would be
All right, I think everybody's back. I just want to take a minute to share the correct numbers with you so you can check your work. It looked like most people were on the second page and a lot of people were getting stuck on 2B. So I'll tell you what equation you should be using for that. But first, for the first problem 1 that you're doing, I got the spring constant to be equal to, and hopefully you're seeing my notability here. I got it equal to 408 Newton per meter. And then you use that spring constant to calculate the force. I got 6.9 Newtons. It's to the left, right? The spring is pulling back that way. So some people made it negative, and that's fine. Okay, the harder problem, I think, was the second one here. And the force over the area, I got about 2.2. You can call it, I had somebody tell me 2.18 times 10 to the 8th Newton per meter squared. Now, that change in length, though, you need the equation I've put around with like a bubble. I've circled it here. Force over area is equal to Young's modulus times the change in length over the length. I think you know everything but that change in length. If you calculate what it is then based on all the other numbers. And again, the only hard part is you got to remember that area is pi times the radius squared. We give you the radius, right? So get that. I get delta L, a little elongation of just a little less than a millimeter, 0.89 millimeters. And then the stress, which is equal to Young's modulus times the strain, would result in a change in length over the length of about 1 times 10 to the minus third meters. Nope, I'm sorry. There's no units there. Dimensionless, about 1.09 times 10 to the minus third. Dimensionless number, right? Strain is a length over a length. Last thing is the stress to break the bone is given. That's the ultimate strength, we call that. And so just solve for the force. You can see it's just about 1.02 times 10 to the 5th newtons. Those are the answers. If you get those right, you're good to go. Upload them to Canvas. Any questions for me? I've kept you 2 minutes over here today. All right, well, everybody have a great day, and we'll see you later on.
I have a question.
I'm sure I can. Is somebody? It looks like Andrea, you're talking right now. I can barely hear you, but go ahead.
It's Katie. Can you hear me now?
A little better. Go ahead.
I have a question about number 1B. We're looking for force.
Okay.
So we found force to be like 408,
Right.
and then we multiplied it by like the change.
The new change. Yes. Okay. So first of all, you said the force was 408. The spring constant is 408.
Yeah,
Right?
yes, that's what I meant. Yeah.
Right. Okay. And so,
And-
but that tells you, and I'll share my screen with you here. Hopefully.
So we multiplied it by like the 0.005.
No, I think if you interpreted the words that way, you could say that that's not what the problem was trying to ask. And it may not be clear, but what it was trying to say is, let me share this with you. Screen mirroring so I can write on something.
Because from the way we like saw it was that the 12 was at rest.
Okay.
And it stretched to 17. So
You looked at a change of 5 then, right?
yeah.
Yeah, let me read it. It says, what force does the spring exert on the block if the string is now stretched to 17 millimeters? Here's how this is the picture. If you're not wrong, if that's the way you interpreted the words, how's that?
Okay.
Yeah. The way I read those words, I said, okay, this distance right here that I just sort of highlighted there, that starts off as 12 millimeters. And then the guy keeps pulling it with that hand until it's out here. And now that's 17 millimeters, okay, to that new distance.
Okay.
Yeah, that's the way I saw it. But, and you already used the 12 in order to get the 408. And so now it's a total of 17. And right, 4.9, if you think about ratios, what we're basically saying, because Hooke's law is a ratio law, isn't it? We're saying that force 1 is to force 2 as the extension, I'll call it delta x here, 1 is to delta x2. And I saw this as 12 millimeters. I saw this as 17 millimeters. And the first force was 4.9 newtons. And so the question is, what's the second force? But if you read the problem as it gets stretched now 5 millimeters extra, and you want it, but that would be, in this case, that would be the block back here is the way I would read it. Okay, less than the original stretch. Okay.
Okay.
Yeah, but I understand what you guys were thinking, and that could be just the way the wording was. But with that picture, I think I would have done my way. All right.
Okay. Thank you.
You bet. Anything else?
I think that's it.
All right. Sounds good. I'll stop sharing this.
Hello,
How you doing, Aberici?
I'm doing very good, sir.
What can I do for you this morning?
I have a question on the homework that's due today. So
Sure,
the
absolutely.
online homework though.
Yep.
So I can like.
Yeah, go ahead and
I'm gonna share my
you should have permission to share. Go ahead and share your screen if you got it.
Okay. Oh. Share. Okay. So let me see. Is this where it is? Okay. So this one. There we go. I eventually got it through trial and error, but I did not understand
All right.
like any coding.
There we go. Now I can see it. Okay. So I've got 4 pulleys with a heavy block and a light block. It looks like on the first 2, the heavy is on the left. The second 2, the heavy is on the right. And so what are the signs of the angular velocity and angular acceleration of the pulley in case A? Okay. I'm going to share my, well, hold it. No, I'm going to draw on your screen. Let's do that. I can do that, I think. Because otherwise your screen will go away. So if this block is going up, right, that means that this thing is rotating that way, right? That's the velocity. Does that make sense?
Is rotating that way?
Yeah,
Or
because if
that's what
this
you're
is
doing?
falling downward, which is what,
Yes.
and this is going up, then the pulley wheel has to turn that way, I think. Okay, and so that tells me that's a
Okay. Yes.
clockwise, and so omega is negative, right? So that makes it either choice
Negative. Yes.
the first one or the last one. And that's just the definition of what we said. Counterclockwise is positive, clockwise is negative. Now, here's the next point, I guess. If this block is the small one and this block is the big one, even though you started it this way, because maybe you push the big block upwards, if you let it go, which I think is what it says, what's going to ultimately happen? Well, I think this, because this block is bigger, that's a big force downward. That's kind of just a little force downward.
Oh.
It's going to slow down, isn't it? Slowing down means the angular acceleration is that direction. And so that means a positive angular acceleration.
Okay.
And so that out of the two that are, that narrows your choices down to that one because it's slowing down because of the where the big block is and where the big block is. Make sense?
Okay.
All right.
Yes. Actually,
All
that
right.
makes like yeah.
Yeah.
Okay.
I'll erase my. I'll erase
Then
my
I had another question.
Sure. Go ahead.
I didn't like this one.
Okay. When you
If you can
stand
see the
quietly, you
question
pivot
and then
and pivot
see
back
the
and forth a
person.
very small amount about your ankles. It's easier to. This could be a significant figures thing. It's easier to maintain stability if you tip slightly forward so that your center of gravity is slightly in front of your ankles. The 66-kilogram man is that tall. Center of gravity is 1 meter above the ground, and during quiet standing, his center of gravity is 5.5 centimeters in front of his ankle. Okay, so I got the picture now. Let me draw it. And everybody's numbers are slightly different. That's why I was kind of, so there's his center of gravity. Okay. And he is, the center of gravity, you're told, is 1 meter up, right? In your problem, 1 meter above the ground. So that distance is 1 meter.
Yes.
And the center of gravity is 5.5 centimeters in front of his ankle. So that'd be 0.055 meters. Okay. So I've kind of drawn it to scale there. Let's put this side over here where I probably should have in the first place. The 1 meter is really right over there, right? And get rid of this one. How come there it is, got rid of it. And we're trying to find the magnitude of the gravitational torque about his ankles. All right. And so his ankles, remember, were back there. That's where his ankle is. We're trying to find the torque. And the only force, I guess, I have to worry about is that one, his weight, about the ankle.
Yes.
So there's his weight, and we know what that is. He's 77 kilograms. So you just take that mass and you multiply it by G. So you get some number there. It'll be about 760 newtons, something like that. That's just a number. Okay, so now we got to find.
Yes.
And that's the hard part here because it's the torque isn't perpendicular, right? R is that hypotenuse, isn't it?
And how do you know to turn to a triangle?
As soon as I saw that they were making this distance horizontal and the other distance vertical, I just said it. I have to. There's right. They meant that to be perpendicular to me. And but the bottom line is I needed that hypotenuse there, and I realized the 2 dimensions that they gave me made that fairly straightforward, right? So R is equal to the square root of 0.055 meters squared plus 1 meter squared. And I think, I don't mean to be, kind of flippant in my answer. I'm not sure I answered your question. How did I know to do a triangle, to make it into a triangle? What I tried to do is take all these numbers, because initially, if you just read it, I don't know that I'd have seen it's a triangle either. But as
Yes.
soon as I started drawing the distances that were given, right? And you notice I drew the first distance right here, which wasn't
Like
the right
500.
place, was it? It didn't help me out
Yes.
much. And then I went, okay,
Yeah.
what can I do? Well, move that over to here and make a triangle so I could figure out that distance R there. Because remember, torque is R times F times the sine of the angle in between them, theta. And it looks, theta's right here, isn't it? That's the angle in between R
Yes.
and the force.
Yeah.
So I'm going to show you something, because you could grind out all these numbers in your calculator and make it hard on yourself, but just stay with symbols for just a second. All right. And rather than writing out numbers, I'm going to call this X 0.055 and this Y. Okay. And that's just because I'm too lazy to write out 0.055 meters. And I mean, that's really the only reason I'm doing that. Okay. So R here, and you'll see why I'm too lazy to do it. I just don't want to. R is X squared plus Y squared, right? That's what R is. The force is just mg, which you're going to calculate because you know the mass, right? And then the sine of theta, that is going to be the opposite side, x, divided by the hypotenuse, x squared plus y squared. See why I was too lazy to write those out? That's in the numerator, that's in the denominator.
Yes.
They were going to cancel, so I didn't need to write them out, did I?
No. Oh my God.
Right? And so the answer is m times g times that distance x that was given to us. And that saves you a step of plugging numbers into your calculator if you see to do that. So that's a little shortcut. Nothing wrong with finding out what R is. Squaring this number, squaring that number, taking the square root. Nothing wrong with that. This is just a little shortcut, isn't it? And we call this distance x, and when you're doing torques, it's the perpendicular moment arm is what we call it.
Radius. Oh, so that's it's
it is the radius times the sine of theta.
Yeah.
Which is what you need. Okay. And so you can calculate it using this middle thing right here. You can put all those numbers into your calculator, or you can go, look, those two cancel. Your choice. And if you don't see a trick like that, no big deal. Your calculator will do it. But if you do see the trick like that, you can save yourself some punching numbers in your calculator. And I always recommend that because there's less likely to make a mistake punching numbers in your calculator with shorter equations, right? Which is kind of the probability. And believe me, that's an old man who's made a lot of mistakes.
Thank you.
A lot of mistakes in his life. So that's my theory. Put fewer numbers into the calculator, fewer chances to hit the wrong digit. Answer your question. Any others this morning? These are good questions. Wish more people would come.
No, I don't have any more questions, but if I do have questions, I'll.
Yeah, I'll be back at 10:30. I'm going to hang around here a little longer. But then there's a number of people that go off to class, and sometimes they come back at 10:30 for questions. So I'll be here through the morning. All right.
Okay. Thank you.
You bet. Have a good day.
You too, sir.
You bet.